How many of you heard of Mobius transformation? I mean, we are more than mixed background, right? So let me know my audience. Okay, so first of all, thank you for the introduction and thank you for INI for allowing me to present my topic. And actually, my talk was in 7th of May, but I got visa late, so I came here. I must thank Joe, who have done all those things for me, because of he shifted this from 7 to 9 and so on. So yeah, so by the name semi-parametric list area linear circular regression through Mobius transformation. So what I can understand is there are two different type of random variable associated, right? One is linear, another is circular. So linear random variable we all know, and circular is when we talk about direction, like wind direction, wave directions, and say for in bioinformatics you will find the torsional angle, the angle between proteins, alpha carbon bond and the other part of the protein. So those are the angles. So those are the random angles. So that those areas are considered as a directional statistics, and circular random variable is among one of them. And so this is a regression problem. And Mobius transformation is from complex analysis we'll use, and list area for it will come from differential geometry. Some tools from differential geometry we'll use to build our own loss function to estimate the parameters associated with the Mobius transformation. And why semi-parametric? Because semi-parametric, because it doesn't depend on any particular distribution. So it is distribution free. Only what we need to do, we need to estimate the parameters of the Mobius map. So this is a joint work with my supervisor, Dr. Buddhananda Banerjee. He's from IIT Kharagpur, assistant professor, and I am his research scholar. So this is the basic outline of my talk: introduction, literature survey, example of the data application, and then regression model, loss function, simulation, data processing, and so on. So the topic involved in this talk, you can see Mobius transformation complex analysis, and loss function we have derived from differential geometry using first fundamental form, angular error from directional statistics, as I have already briefly mentioned. And we have find the confidence interval for using non-parametric bootstraps, and then you have used this LBFGSB optimization function for optimizing our estimating our parameters from Mobius map, and then we have apply our regression model to the data associated with the cryptocurrencies, the well-known cryptocurrency Bitcoin and Ethereum. So this is the basic introduction of directional data. So there are circular data, toroidal data, cylindrical data. So for toroidal data, I have already mentioned bioinformatics, protein diagonal angle, meteorology, wind wave direction, you can see. And for cylindrical data, in climate, wind direction, wind path, wind speed, that can be modeled as a cylindrical data. And another is in finance, time of occurrence of high and low value of the stock, and the value and the time. So time will be represent as a circular random variable, and the values will be represented as a linear variable. So we can get a cylindrical data. Now come to our linear circular regression. So this is a relationship between circular or angular random variable and linear variable. The response variable here is angular, and the predictor variable is linear. And by effectively linking these two linear circular regression, we offer a valuable insight that sometimes this linear regression cannot do, because it doesn't consider the topology or geometry of the data. So this is the general Mobius map, a very basic Mobius map that preserves circle and angle in an extended complex plane. That is defined by fz equals to az plus b by cz plus d, given that ad minus bc is not equal to 0. And this can be further decomposed in these three fundamental map: translation, scaling, and inversion. I'm not going in details for this map. So some literature review. So first, back in 1996, McCobb he just introduced Mobius map associated with Cauchy distribution. From that he derived Rab-Cauchy distribution. So that is the first use of Mobius map or complex analysis in directional data. Then after that, many other authors like Donson, Mardia, Dons, Kato et al., they have introduced Mobius map for different aspect of directional data. So for regression analysis, they have used Mobius map 2008, 2003, 2002, and Jahan Biswas, they have recently 2018 they have used this Mobius map again for circular regression but for zero spike data. And for linear circular regression, so far these are the no, I can say this is two. This is 1992 and 2015. These two paper only available to our knowledge that they used, but they do not use Mobius map, but some link function they have used called tangent function. And for Kim and Sengupta, they have used specific strographic projection as a link function. Now come to our data. So Bitcoin we all know, and so we have taken the data from Kaggle, openly available, and the data we have analyzed is from January 2017 to July 31st, 2017. This data we have analyzed. Again, the Ethereum. This is another cryptocurrency data, and we have taken another the data from January 2018 to July 31st, 2018. So whether we want to check whether there is any relationship between this Bitcoin and Ethereum or not, but so that's why the same time we have taken but different year. And these data set considered unique timestamp, date, symbol, opening price, lowest price, highest price, closest price, and so on. So later on in the data analysis part, I will show you how we have processed our data for our purpose. Yeah. So now the right corner, the first one, that map, that is a specific Mobius map that maps the upper half plane to circle. So z minus beta 1, z minus beta 1 bar, where this beta 1 belongs to C, beta 1 belongs to unit circle, that is nothing but a rotation parameter. But what we want to do, we want to do linear circular, right? So that's why instead of z, we are considering x. That means for z, there is no imaginary axis. So imaginary part is 0. So we are considering the real part only. So beta naught x minus beta 1 by x minus beta 1 bar. So again the parameters specification as same as the earlier one. Here is a pictorial depiction of that from R, the real line. How using this map we got the circle, right? And this is okay. Now interpretation of this beta or beta 1 is beta naught is quite straightforward. So it is a rotation parameter. So whatever data is, it rotates in certain angle. But beta 1 is quite difficult. But one important observation you can see, if this mod of beta 1 they goes to 0, you can see the argument of that map, that means the angle, they are coming to 0. So you can see figure number 6. From pi by 2, the points are coming near to 0. So that is one of the interpretation of beta 1. And again the beta naught, if you see beta naught is 1, then this is the figure, and beta naught is not 1, then that is the figure. So eventually that is the rotation. Now let us propose our model. So this is the model. Theta is our response variable, belongs to 0 to 2 pi. As I already said, that is angular variable, and x is real number. So argument of that map plus epsilon. Epsilon is a random error here. So this gx, that gx beta naught, we call it link function, and beta 1 again from unit circle. Beta 1 is beta naught is unit circle, beta 1 for a complex plane. Epsilon is a random error with 0 mean and fixed variance. So why 0 mean? Because we want to draw the analogy from linear regression. So for linear regression, we all know we usually take this epsilon belongs to some normal distribution 0 and some non-variance, and for individual data the errors are IID. So this is the pictorial depiction of the whole model. So from data drawing from normal 0 1, then we are giving the transformation, then we are adding this noise VM03, that is von Mises distribution, which is the maximum entropy distribution in circular data. Okay, so we have drawn derived our model. So now what we want to do, we want to estimate our parameters, right? So for that we'll define our own loss function, and that is inspired by this loss function in real random variable. So yi is observed value, yi hat is observed predicted values. Then the loss function can be defined in this form: L equals to minimum of that mean of that loss, mean of the error. Now if we look carefully, we can write capital Y square is equals to that, small y minus small y square. So and eventually what it becomes the mean of random square areas. So if you look carefully, and the area of the rectangle, area of the square, the arm length is y, right? So so we just want to draw this analogy to our purpose. Now here we have angle. So instead of y square, we will have theta square, right? But what is theta square? If you have an angle, what is the square of an angle? If you don't think about it, the linear one, if you think about the angle, right? So theta square, if you pi square won't be in the circle again, right? So then you have to do mod 2 pi so that it get back to the circle. But for theta square and the product of two angle, we have derived a new thing called square of an angle, and that one will come very soon. For that we need torus. The torus, the two-dimensional curved torus given by the equation 3, and that parameter space phi theta, they belong to 0 to 2 pi. They are that called flat torus, right? Now the any area between 2 point phi 1 theta 1 and phi 1 theta 1 and phi 2 theta 2, phi 1 theta and phi 2 theta 2, that can be decomposed in 4 ways. So you can say, oh, so another thing is this vertical two vertical they are identified, and the horizontal and the upper one, that they are also identified, right? So that's why you can see this is how the areas are calculated. So this is the 4 areas of the flat torus, and corresponding to that, using differential geometry and some tools from that, first fundamental from an area element, we have calculated the areas on the curved torus. So let me show you by the figure. So this one, the right figure. That is the area you have seen in this flat torus. The corresponding areas on the curved torus is like this. Right? Now what I have shown you so far, this is for any general point phi 1 theta 1 to phi 2 theta 2, right? But for our case, what we have seen in our square error loss for linear random variable, that is a area bounded by 0y and 0y. I mean, that is square area of area y square. Yes. So that's why we need to calculate the same thing from 0 0 to theta theta, and this is the calculation for that. Now we will going to define square of an angle. So for that, first of all, we have 4 areas. Now what area we should choose, right? So we have to be careful for that. That's why we have taken minimum of all those areas. And why minimum, why not maximum? That is that question can be asked. But the thing is, equivalent is geodesic, the shortest length between 2 points in any surface. So like that, we have considered the minimum one and divided it by 4 pi square at the entire surface area. Okay, so that we can get rid of this smaller capital R. And 2 observation are, you can see that if you sum them up, you will get the entire surface area of the torus, and that proportionality area is bounded by 0.25 always.
So and can I ask you, so what is little r?
Okay, yeah, nice question. So small r is the so you see this is the torus. The two circle, there is a horizontal circle and vertical circle. So small r is the radius of horizontal circle, that is the smaller circle, and capital R is the radius of the horizontal circle, and small r is the vertical circle. Yes. So now we define a square of an angle given by this definition 2. So now we will use this square of an angle to minimize the loss function for our proposed linear circular regression model. For that, let this theta and xi, the point come from cylinder, as you can see, si cross product r, and the expected value of theta is given to this. And now this is the error for the model, true value theta I, and expected value expectation theta I given xi, and we are doing modulo 2 pi. You can use module 2 pi, or there's another formula, you can use that. Whatever you choose, it will work. We have used module 2 pi. So now this is our loss function, that we want to minimize this loss function to get the beta naught and beta 1.
Can I ask a question?
Yeah, sure.
So when you're working on this manifold, which is the sphere or the circle in your case, can you connect your square of an angle to things like barycenter, Wasserstein barycenter, or sort of geometric features of sort of averages for points on the sphere, or is there some connection or not at all?
Yes, we haven't explored that one. Basically, right now, what we are doing, we are working on torus, sphere, and circle itself, and not more beyond that. And we haven't considered that one. This is whatever you just said. This is a part of my PhD thesis, so I'm still working on it. So yeah, so this is the loss function we have developed, and we call it mean square angle error. So because we want to minimize the error between two angles, and then we have used LBFGSB to get the estimated value of that. And if you see the simulation, you'll see it perform quite well. So for simulation studies, we have taken three sample sizes. For small sample behavior 50, mid moderate 150, and large 50, and you can take more than that also. And two different distribution we have considered for our angular error, because we want to show that it doesn't depend on any distribution, and we don't want to minimize or we don't want to estimate any parameter from any distribution. And the mean direction said to be 0. So in that panel, so you can see that x is coming from normal 0, 1, that is our covariates. For that, we have considered random error from von Mises distribution. Why this? Because there is a relation between von Mises distribution and normal 0, 1. So von Mises distribution can be approximated as a normal 0, 1. No, normal distribution, not 0, 1, normal distribution. And Rap-Cauchy again from as I have already shown back in 1996, from Cauchy to Rap-Cauchy using Mobius transformation, Magov given that given that away. And another thing is for simulation, we haven't estimated the values beta 1 and beta not explicitly, but we have done B1 plus I beta 2 because of the computational simplicity. So now these B1, B2, they are real numbers. So we don't want to work with complex number now. So and this the right parallel two figure, you can see the first one, the residual plot. So you can see no systematic trend or symmetric around this zero degree angle, and we have done Watson test, and that Watson test is to check whether the data is coming from von Mises or not. So you have seen this is coming from von Mises distribution, and this is the figure 13. What you can see here, that true regression curve is red color, and the estimated volume is blue color. So they quite, you can see from the figure, they are quite, overlap with each other. This is the table for that. And if you see, as the sample size increases and kappa increases, the estimation of beta B1, B1, B2, and B0, they are getting much better than the previous one. So and the random standard error also getting less. So this table is for von Mises distribution, and this is the same thing for Rap-Cauchy distribution. Again, here same trend can be seen. Now we have used non-parametric bootstrap method to derive confidence interval and prediction interval. So not like linear data, confidence interval can be seen in two ways, because 0 and 2 pi they are same in circle, right? So you can see, so the figure number 14 and figure number 15, they both are confidence interval for this mu hat for true population mu theta j. And there is yes, this is the algorithm for that. So we have used non-parametric bootstrap for calculating confidence interval, and similar another algorithm for calculating prediction interval.
can ask another question?
Yeah, sure.
So your confidence interval, so it boils down to looking at sort of the geodesic distance, like it's or nothing.
No. So now come to data processing for our data. So we have taken, I have already told you that we have taken data from Ethereum and Bitcoin. So first let me explain by the figure. So this is the plot for maximum price per minute for the day 31st December 2017. So this is the plot of the data, the value of the Bitcoin data. So you can see that that red dot, they are the per minute highest value. For entire day, that intersection point, this dotted line and this dotted horizontal and this solid vertical line, that is the highest value, right? So corresponding timestamp is near 200. We have taken that timestamp when converted in angle using this formula. So this formula what eventually give you for a particular day when the maximum happens, then we have converted in 0 to 2 pi. That is our, now this is our circular data. So that's mean time can be again modeled as a circular data. And for predictor, the particular function we have made. So L, H, C, O, they are like lowest price, highest price, closing and opening price. And one may ask why particularly this one, why not another one? So yes, you can take another one. We have taken another one also, but we right now we don't have any particular formula for the what will be the our predictor or covariate. So this is simply the plot of the predictor, and this is the circular plot of the time that modified as an angle for Bitcoin and Ethereum. Now this is the values, estimated values of the parameters from the Mobius map. So you can see the standard errors are also there, and the correlation then is calculated. And this is the pictorial depiction of QQ plot that observed and the estimate and the predicted values. And that figure number 21, that is the residual plot. And again we have test whether it is from any particular distribution or not. So eventually it is from von Mises distribution. The Watson test, from Watson test we can get that. And this is for Bitcoin. So the last one for Ethereum, and this is for Bitcoin. So again QQ plot and the residual. And so in conclusion, what I can say that we have used Mobius map, generalized Mobius map, not only Mobius map, for linear cycle regression. The model is semi-parametric, and area-based loss function using differential geometry we have introduced, and real-world data involving Bitcoin and Ethereum we have analyzed for the model. And this is the paper that is published, statistical analysis and data mining, and these are a few references that I have used in my paper. Thank you. If you have any question, I am happy to take it.
Any questions?
Yeah.
Yeah.
Just, I didn't understand why you take.
Hello? Yes. Yes. हाँ हाँ अभी आप 3:30 पौने 4 के अंदर आ जाओ, 4 बजे और
There is an interference in the line, but go ahead, Clémentine.
Just can you come back to the definition of the square of the angle?
Yeah.
I didn't understand why you take the minimum of the errors in the
Yes, sure. Here?
Yes. Why? Can you explain why you take the minimum? I missed that part.
Okay, so there are 4 areas, or just in that A1, A2, A3, A4, right? Now, why minimum? So for any 2 point you take in any surface, so that is geodesy concept of geodesy, like minimum path or minimum energy function, right? So and we have drawn the analogy from that. That's why we have taken minimum. That's it.
Thank you.
Yes, sir.
So, could a regression curve be dense in the torus?
That is a
Because especially when you are looking at confidence bands, then you run into this, that your estimate might get to be a dense curve.
yes. Yes. Thank you for the question, but we haven't checked that one. Just
It's a problem.
yes. Yeah, we'll definitely keep in mind.
Any other questions?
Yes, thank you for the talk. I missed the point about the reason why you use this transformation and why not a simpler one, because Möbius transformation is highly nonlinear. It is a ratio of the exponent. Why not simply using R cosine and R sine, something like that?
So, I mean, just let me. So you are asking that why we have used Möbius map, right? Instead of taking some simpler function to do the regression, right?
Simpler models with your data, for instance.
Yes, simpler model for that. Okay, that is a really good question. So, the general definition of Möbius map. This map preserves structure from circle to circle, or circle to sphere, circle to straight line to circle in complex plane, right? And so this particular one, that is from real line to circle, right? Now here we have used the geometry of the data. If we take some simpler maps, we may need to do modulo of 2 pi. So there are couple of models, especially for circular regression. What they have taken, they have used linear regression, then they have done the modulo of 2 pi. So there is another paper we have worked. So there we have shown that if we consider the geometry, then the fitting goes very well than if you don't use the geometry of the data. So just because of the geometry of the data, and since this Möbius map, they do not, they preserves the structure in the complex plane. That's why you have used it. Because we want to keep in mind that we shouldn't move from the space.
Thank you. In the interest of time, yes.